Hello, everyone. Today, I'm going to talk through our journey of improving regression performance. We started with a standard baseline and systematically optimized our approach to balance bias and variance, and ultimately arriving at a high-performing cat-boost model. We will look at the specific techniques we use to reduce error and combat overfitting. Every optimization task needs a reference point. The first, initial configuration. We began with a standard gradient boosting regressor. This wasn't intended to be the final model, but rather to establish a benchmark, mean absolute error, MAE score, that we needed to beat. And second, evaluation strategy. We initially used a five-fold cross-validation strategy. This helped us understand the general complexity of the dataset. However, the initial performance metrics suggested that a standard boosting implementation wasn't powerful enough to capture the nuances of the data, promoting us to look for more efficient frameworks. In order to improve the performance, we first transitioned to LightGBM. LightGBM was chosen for its speed and ability to handle nonlinear feature interaction more effectively than the baseline. We noticed the target variable had a significant skew. To fix this, we applied a log1p, log plus 1 transformation. This stabilizes the variance and makes the optimization landscape smoother for the model. Inverse transform. It is critical to remember that because we trained on log data, our raw predictions are also log scale. We applied example1, inverse log, to the predictions to transform them back to the region scale before calculating our final MAE. So with the powerful model comes the risk of the overfitting. We address this directly using early stopping. Instead of letting the model run for a fixed arbitrary number of rounds, for example, like 1,000 iterations, we monitored the validation MAE after every round. If the validation score stopped improving for a set number of rounds, we halted training immediately. This ensures that we use the model at its peak generalization capability, rather than over-memorizing the training data. Here is a visualization of why early stopping was necessary. If you look at this chart, you can see the training MAE, the bottom line, continues to drop indefinitely. However, the validation MAE, the top line, hits a minimum and then start to flatten or even rise. That diverged point represents overfitting. By visualizing this learning curve, we configured that we needed to limit the number of boosting runs to prevent the model from learning noises. So once we fixed the training duration, we focused on robustness, hyperparameter tuning. We manually tuned parameters specifically designed to limit model complexity. This included reducing number/leaves and max/depths, and increasing reg/alpha and reg/lambda regulation to penalize complex rules, and cross-validation update. We also realized that five-folds weren't enough to be confident in our stability. We switched it to 10-fold cross-validation. This reduced the variance of our evaluation result and gave us a much straighter, more reliable estimate of how the model performs on unseen data. Our final major shift was moving from LightGBM to cat-boost. The problem is, in our previous approach, we treated categorical variables using one-hot encoding. This creates a sparse matrix and high dimensionality, which can be inefficient. So the cat boost handles the categorical feature natively. We pass the raw categorical columns directly to the cat/features parameter. So the result is going to be cat boost use a technique called ordered boosting to encode these categories, which capture the interaction much more better than our previous one-hot encoding method. So here is the final comparison of our performance. The baseline, as expected, the initial GBM had the highest error and variance. And the second, the LightGBM. Tuning and log transforms significantly dropped the error, the middle bar. And the last but not the least, cat boost, the final model. Utilizing native categorical handling, the 10-fold CV validation, achieved the lowest mean absolute error, MAE. Ideally, we also see a lower standard deviation across folds here, indicating the model is not just accurate but stable. So to wrap up, here is a receipt for our improved performance. First, log transformation, handle the skewed target data. Second, early stopping, prevent the model from memorizing noise. And the third, native categorical handling. In Cat Boost, replace inefficient one-hot coding. And the fourth, rigorous tuning of regulation parameter kept the bias variance trade-off in check. The result is a model that is both highly accurate and generalizable. So that includes a presentation on our regression optimization pipeline. Thank you for your time.